Have you ever wondered why some machine learning models seem to learn too much from the training data, becoming overly specific, while others remain just too general, missing important patterns? The answer often lies hidden in a fundamental concept called degrees of freedom. Degrees of freedom directly influence statistical model performance by determining a model's complexity and flexibility. A model with too many degrees of freedom risks overfitting, capturing noise in the training data, while too few can lead to underfitting, failing to representing the underlying patterns accurately. Balancing this flexibility is key to building models that generalize well to new, unseen data. In statistics, degrees of freedom can be intuitively understood as the number of independent pieces of information available to estimate a parameter, or the number of independent ways in which a system's configuration can change. For a statistical model, it represents the effective number of parameters the model uses to fit the data. More parameters generally mean more flexibility, allowing the model to trace more intricate relationships within the training set. This flexibility is a double-edged sword, directly impacting the bias-variance trade-off. A model with high degrees of freedom typically has low bias but high variance, meaning it fits the training data very well but performs poorly on new data. Conversely, a model with low degrees of freedom might have high bias but low variance, simplifying the data too much and missing key relationships. To practically manage degrees of freedom, you can employ several strategies. One effective method is regularization, which adds a penalty for model complexity, effectively reducing the effective degrees of freedom. Techniques like lasso and ridge regression achieve this by shrinking parameter estimates. Another approach is careful feature selection, choosing only the most relevant variables, thus limiting the number of parameters the model needs to learn. Cross-validation is also crucial. It helps assess how well a model with a given set of degrees of freedom will generalize to new data, guiding you toward an optimal balance. Understanding degrees of freedom also extends to model comparison. Information criteria like IC, the Akaike Information Criterion, and BIC, the Bayesian Information Criterion, explicitly incorporate degrees of freedom into their calculations. These metrics help statisticians and machine learning practitioners objectively compare different models, penalizing those that achieve a good fit purely through excessive complexity. By considering these criteria, you move beyond just training error to select models that are parsimonious, meaning simpler yet still powerful and predictive. Ultimately, recognizing and strategically managing a model's degrees of freedom empowers you to navigate the delicate balance between capturing essential data patterns and avoiding the trap of memorizing noise. This critical insight allows you to build robust, generalizable, and efficient statistical models that perform reliably on real-world problems.